please consider sponsoring me on Patreon. Link is in the description. You'll be helping me to build open source innovation automation solutions and also develop a low-cost 3D metal printing project as documented on my other YouTube channel, Calabal CNC. Thank you. In this video series, I will walk you through how to build a bleeding-edge automation framework as a single-source multi-testing solution. The goals will be to automate API, that is Application Programming Interface testing, and also UI, User Interface testing, through a single integrated framework codebase. The common framework codebase will also be used to build the release package as part of our CICD strategy, in addition to executing API tests, UI tests, and/or other automated activities and workflows. I will assume that you are familiar with programming languages, in particular JavaScript, ES6 syntax. There are a lot of different programming languages and a large variety of automation solutions, in particular testing automation solutions, for both UI and API testing, performance testing, load testing, etc. In particular, I originally built this same architecture you will see implemented in this devlog series on the HP UFT, that is Unified Functional Tester. It's the same testing solution derived from HP QTP, which is the Quick Test Professional, which itself is derived from Mercury Interactive, for those of you who have been around long enough to know what that is. The original solution was written in VB, Visual Basic Programming Language. I have built this testing solution on all three of these older testing execution platforms. So this architecture has been around for a long time, although it has evolved significantly. You might find some of the design and architectural practices used in implementing this framework very different from what you are used to. I am not forcing you to use my architecture. If you don't like it, you're still free to use whatever tools and platform architectures you want to use. I simply provide this design architecture implementation because I have found it to be many times more powerful than any other framework I've seen implemented at actual customer sites. The reason for this is because it is a data-rich architecture and can scale easily to very large enterprise business needs. And the reason for this is because this architecture significantly reduces the cost of developing test scripts, test cases, and also, more importantly, significantly reduces the cost of test case maintenance. There are a number of innovations that empower these cost reductions, such as top-to-bottom modular architecture and a system of systems design approach that incorporates advanced systems integration. All of these will be covered in detail. I'm a big advocate of following the testing pyramid, as you can see here. That is the principle that most of the testing should be done at the unit testing level, written by the application developers. This helps to identify bugs at the earliest possible time, which is part of another tech industry called shift left, which I show here. So all of these links will be provided at the end. To identify application defects as early as possible to reduce downstream costs. The later a defect is discovered in the Sdlc, that is the software development lifecycle, I'm also showing the systems development lifecycle, the lower the cost. So you can lower the cost by following an organizational strategy that works to identify defects as early as possible. As such, you would then have a slightly lower number of systems integration tests, API tests, and then a slightly lower number of user interface tests. All of that is part of the testing pyramid, of course, and even a smaller number of manual tests. So that's coming back to this test pyramid. So those UI and manual tests should be the smallest number of user interface tests, or the smallest number of total tests. So your organization should not have 50,000 UI tests and just 5,000 unit tests. Such a scenario is an upside down pyramid. It would turn this upside down. And of course, that is not what you want for an organization, because unit tests, the cost of maintaining and developing unit tests is a lot lower than the cost of maintaining and developing UI tests. And service API level tests is, of course, going to be in the middle. So with it, you want to have a corresponding number of API tests. So this, of course, details on API testing, graphical user interface testing. There's articles, all of this, testing automation, more details here, and, of course, software testing automation frameworks. So I'm not going to go into what a framework is. I'm also a big advocate for CTD, that is combinatorial test design. Although we will not immediately implement a CTD solution, I will discuss it here because I have a plan to keep it under consideration as part of the design, so we can leverage an integrated CTD solution in the future when this framework reaches a higher level of maturity. Before giving you any additional details on CTD, I'd like to make a call for collaborators who are willing to work with me on doing additional systems integration with some of these additional innovations. If you are willing to collaborate and follow the overall design approaches outlined in this series, then feel free to message me on any of the platforms linked below, YouTube, Twitter, or Facebook. So the idea of CTD is best explained with an example. Let's say you are running a large business that builds boats, ships, yachts, etc. Your company has a website that lets customers choose options for the kind of boat they would like your company to build for them. Your website has options for the type of engine, leather interior, trim of wood, brass, silver, gold, steel, and delivery options, payment options, etc. Your company has certain limitations of payment, such as your company will not accept American Express credit cards. Also, your company cannot deliver boats to overseas locations such as France with overnight shipping. Now you need to test every single possible combination of options and business limitations you have established as part of your business. Of course, I didn't list every single option, but you'll need to test the V8 engine without the leather interior and silver trim and the loan application process. Then you'll need to test the V10 engine with the leather interior and the brass trim and the Visa payment process. So on and so on, you'll need to test each and every single combination. Perhaps your business is much larger than this simple example, and you have about 2,000 different options your customers can choose from. If you were to write a test for each and every single possible combination, that is roughly 2,000 factorial combinations, which is a number that is larger than the number of atoms in the entire known universe. This is where CTD comes into play. I should also add you're going to need to test against every single mobile device and every different operating system and every different type of browser. Very clearly, that's going to explode to a number that is untenable. You cannot test and write that many tests and execute that many tests. It would take the length of the time of the entire known universe, billions of years, to accomplish this, so you can't do it. CTD, combinatorial test design, is based on the idea that 99% of every bug ever discovered, fixed at every industry around the whole world in the entire history of business tech systems involves, on average, about 3.7 business options. That is, on average, a bug will incorporate 3.7 business options. So if we can write tests that just test combinations of 3 business options, we should still get 100% code coverage with our test plan. The trouble is, how do you identify which combinations of 3 business options should be grouped together to build a test plan? With a CTD system, you build a data model of your business options and limitations, the rules, etc. The CTD system then approximates those business rules and limitations as a system of linear equations. These equations are then combined in a matrix and solved in the same way you would solve a matrix of equations using standard linear algebra. The result is another matrix, but it turns out the output matrix is actually a test plan that gives you all the information you need to determine what combinations you need to test with. This is an optimized test plan, and you can dial back how much the test plan you implement to get the lowest hanging fruit. The CTD system can be integrated with the rest of the testing automation system, such as with another set of business rules that output matrix can be converted automatically into Gherkin code feature files. Finally, rather than implementing a trillion test cases, you might have a list of a few thousand test cases to get that 100% code coverage. So these are some documents on combinatorial test design. Of course, the Wikipedia. There's also known as all pairs testing. Okay, so next. There are many other videos out there about testing, what a testing framework is. Again, I'm not going to go into that. I'm not going to bother going into additional details other than just to state that a testing framework is a set of tools that makes it easier to write automated tests. The difference my framework provides is to remove as much of the complexity of writing script code away from the test developer. This means the test developer can focus on writing tests and not on writing code. This is a low-code, no-code testing automation hybrid, data-driven, keyword-driven, TDD, ATDD, BDD, data-rich framework. However, that does not mean that test developers and test framework architects cannot still write code. Quite frankly, the opposite. It's just that where they write the code, how they write the code, and what code they write is now different than traditional testing automation frameworks. Again, if you don't like it, then don't use it. You are always free to continue using your old framework. Nor do I force you to continue watching my video series, so don't bother commenting how you disagree with my engineering approach. You are free to implement your own framework as you would like, or show me how I can do better. I'd be happy to collaborate with for the best of the project so we can all improve through appropriate focused innovations. Of course, this is an article on test-driven development. We have acceptance test-driven development and behavior-driven development. So if you don't know what those are, feel free to read the articles. And even if you do know what they are, it might be good to refresh yourself as well. I should add that I've put a special emphasis on where, what, and how code should be added to the testing framework. It has been my experience that when a team of developers start adding their own code to the testing framework, very often the pressure of delivery forces developers to implement what they need for their own test delivery requirements. But what they implement is never communicated to the rest of the team. As a result, other developers don't fully understand what has been implemented, or what was implemented was done in a way that might be slightly different from what future needs are. So the next time a developer needs something similar, they are either forced to implement their own similar solution, or they don't have time to understand what was already developed, so they move forward with their own solution anyways. Either way, the result is duplicate code that must now be maintained. The same thing happens with new hires come on board the company or the project. Eventually, there are potentially many duplicate versions of the same code, and the result is an exponential growth of technical debt. That can derail an entire framework or test enterprise, or ultimately force a complete restart for the company of the framework or the development code. And I'm sure if any of you are software engineers, you know that this and have experienced it. I've actually seen it happen. So the problem is ultimately known as an emergent behavior. An emergent behavior is a behavior that is only observed when multiple actors begin to interact given a specific defined architecture or set of rules. An example of an emergent behavior would be to take a bird in space. It will fly around in that space, but as soon as a bunch of other birds are added in the space, they will fly in random directions. However, as soon as you tell the birds about each other and that they should avoid colliding and yet follow each other in the same direction given some threshold values, etc., there's a bunch of rules, right? Then suddenly all the birds will flock together in the same direction, turning this way and that together. Dustin on Smarter Every Day did an awesome episode on emergent behaviors. It turns out if you change the framework architecture, then the emergent behaviors will also change. It is possible to discourage bad emergent behaviors and encourage good emergent behaviors simply by changing the framework architecture. So the architecture I've chosen is to do just that. Additional design principles we will follow when writing the framework code are the clean code principles. We have DRY, stands for do not repeat yourself. Essentially, if code is used more than once, we will refactor it ASAP and attempt to design for additional code reuse. YAGNI, Y-A-G-N-I, you ain't gonna need it anymore. If code is commented out, we will try to remove it ASAP to keep the code clean. SOLID, single responsibility principle, open-closed principle, Liskov substitution principle, interface segregation principle, and dependency inversion principles. You can read about those here. Additional clean code principles, we're going to have those linked below, and all of these articles are linked. Other important considerations I've made when deciding the tool chain for this framework are the need to have an execution engine that is based on modern web standards. Essentially, that is your browser hooks, and almost everybody who's in testing automation understands this to be the Selenium web drivers. Essentially, those same hooks can be used to drive from any automation execution engine. But the important thing here that I'm trying to get to is we don't want to or have to need to translate between browser native JavaScript to Java and then back to JavaScript or TypeScript. Since most of the web is written in JavaScript and there is some compatibility between JavaScript and Python, I've chosen to implement the framework using JavaScript and leveraging the ES6 ECMAScript syntax. So some links on JavaScript and ECMAScript. Looking at execution engines that support this language, we still have a large number of options. To narrow it down some more, I wanted a testing execution engine that will fully support async await promise to maximize future extensibility and parallel test code execution. Furthermore, I want to choose a framework that would let me inject and execute client native code on the browser client and be fully open source. The best solution I've found to fit all these requirements is Test Cafe. And of course, we have the regular Python links and tutorials. To continue the discussion of emergent behaviors, we must also discuss some more about the Sdlc. I want to clarify software development cycle. When we're talking about testing automation, it should actually be considered that we want to consider a testing automation solution is not written using an Sdlc. It's written something called an ADLC, which is an automation development lifecycle. But the terms apply very similarly in the sense that an Sdlc is going to have follow a CICD platform. An ADLC should also have its own CICD platform as well. But to continue on, specifically on the topic of Agile versus Waterfall, which is the point I'd like to focus on next. I must specifically call out object-oriented inheritance as a waterfall approach to software engineering. OOP, object-oriented programming, is not an Agile approach. Now granted, I recognize there are places and situations where OOP must be used, such as military hardware, avionics, nuclear power systems, and other embedded applications. However, for most software engineering applications, desktop native, mobile, and cloud applications, an OOP, object-oriented programming, is not the best approach because most of these applications are being executed or being developed in an Agile environment. As such, implementing them using an OOP approach not only limits the effectiveness of the Agile approach to the Sdlc, but also limits the ability of the cultural shift to Agile within the organization. Let me explain. Let's say you have a company that makes a software that lets users of vehicles model their vehicle on their device. You've spent a large amount of time building your application and it's been well received in the automotive industry. However, now Boeing has approached you and wants their pilots to model their aircraft using your software. So you tell your engineers they will need to support 3 wheels rather than 4, and your wheels need to be retractable. The engineers come back and tell you it would take a long time to redesign the vehicle interface. The developers explained that they never designed the object-oriented inheritance model to be able to support 3 wheels. Now you have to go back, and the changes will have impacts to all the vehicles because they will have to issue a new class interface, and all the old cars implementing the old interface will need to be migrated over to the new interface. This further imposes testing and deployment restrictions for future versions to certain customers who have government requirements, such as those customers who are using your software to model military jeeps. After a few years of building and implementing this new interface, the British Royal Navy now says they want to use your software for their amphibious vehicles, which have 6 wheels that are retractable. Again, your developers come back and say the whole inheritance model needs to change, and yet another interface will need to be issued, and you're back to the same problem again. This is because car and airplane objects inherit from another class object called vehicle. So if your vehicle model changes, then your car objects and airplane objects could potentially be impacted. Granted, there are ways to design for this, so it is a greatly simplified version of the problem. And these problems do exist, although in a much more complex technical business environment. The point is that with OOP, you design an inheritance model given a set of requirements, perhaps trying to think ahead of ways the model could be used or reused in the future to anticipate future changes and requirements. Then you implement a system based on that inheritance model and those list of requirements. When changes come along that you did not anticipate, then you have to change the design model and also handle impacts to the implementation. All of this adds overhead to your development and deployment and customers. If those requirements are changing continuously, as they should be in Agile, then you are constantly changing the inheritance model and constantly dealing with impacts, and your overhead grows exponentially and can quickly become overwhelming. In comparison, a composition model works like this. A customer comes to you and says they need to support 3 wheels that retract. So you have a wheel object you've implemented and a chassis object. You grab them off your virtual shelf of solutions and implement them to make a vehicle model that supports the customer's needs. There is no inheritance model and no need to handle impacts. When your customer comes and says they need 6 wheels that should retract, you just copy-paste your wheel object 6 times. You write a new model to support the retracting of those wheels. If that same customer comes back tomorrow and asks for 5 wheels rather than 6, you make a quick change and you've instantly met their requirement without any or hardly any overhead or impacts. This is an Agile approach. As such, this framework will be developed with the concept of composition over inheritance, which is a well-known and long-standing principle of software engineering. It turns out that JavaScript was built with this concept of composition over inheritance in mind. It is true that JavaScript does support the use of this keyword, and it also supports the use of classes, objects, and inheritance. However, it makes it difficult and a little risky to do so. Please reference the blog article, The Many Faces of This in JavaScript. Another interesting and difference you may notice with this framework implementation I will do as part of this video series is some very unique names for files, modules, and functions. I do this because I read about some blog articles called I shall call it something manager, and naming classes, how to avoid calling everything whatever manager. Okay? Again, these are links that will be below. Additional resources for reading and skilling up. I will be doing the best to follow the principles outlined in each of these books throughout the entire implementation process. If I ever misstep, please feel free to call me out. See the links in the video description. Clean Code, a handbook of Agile software craftsmanship, 7 habits of highly effective persons, the 8th habit, Clean Architecture, a craftsman guide to software structure and design by Robert C. Martin, and The Clean Coder, a code of conduct for professional programmers. All very good books and articles. If you find this video helpful, please click the like button below and click the subscribe button and the bell to be notified when new videos are published. This also helps me out and lets YouTube know that you enjoy my videos. Thank you very much.